Onward. So, armed with the knowledge of rep, we can write an illustrative example of generically deriving eq, the equal type class. Of course, it's unnecessary because eq is one of those classes the compiler can write for us. Nevertheless, it's a good introduction to the topic, and we must walk before we can run. We'll look at more challenging classes afterwards. The approach to generically deriving structural polymorphism is threefold. First, define a type class to act as a carriers. I don't know what that means yet. Maybe I do, but I don't remember it exactly. Provide inductive instances of the class for the generic constructors. Finally, write a helper function to map between the rep and the desired type. We begin by defining our carrier type class. The carrier mirrors the type class we'd like to derive, but is shaped to be able to give instances for the rep constructors. A good convention is to add a G prefix to the carrier type class. If you want to derive eq generically, call your carrier type class geq. Okay, so we're gonna do that. Class geq a where geq ax bool. Okay, so basically, actually, I kind of want to put this book over here. It's in my way. And there we go. Okay, so this kind of looks like eq, right? You have an x, and you return a bool. The only difference is that we need to wrap these things in rep. So I guess that's where that a comes from. Okay? And, you know, this eq and this eq look very similar to the type classes. Notice the type parameter a to geq has kind type to type. This is a quirk of GHC generics and allows the same rep machinery when dealing with higher kinded classes. When writing carrier classes for types of kind type, we will always saturate A with a dummy type X, whose only purpose is to make the whole thing kinda check. Oh, okay, I see. So actually this X is the dummy parameter, not the A. I get it. I misunderstood that. With our carrier defined, the next step is to provide instances for the generic rep constructors. A good approach when writing generic instances is to work inside out. Start with the innermost constructors, U1, V1, and K1. I don't really remember what that means, but hopefully it will make more sense here in a second. In this case, U1 is the simplest, so we will start there. Recall that U1 represents a data constructor with no parameters, in which case it's just a unit with a different name. Since unit is always equal to itself. Oh, right. Okay, so U1, V1, and K1 are like unit, value, and kind, maybe? We'll see. Maybe it'll make more sense here in a second. So now we just start writing these instances. So instance geq u1 where geq u1 equals true. Oh, right. What is it? ZT. There we go. And actually, it should be that. Can everyone read this okay? I hope so. I think it's big enough, but I can make it bigger if necessary. Okay. So, similarly for V1, which corresponds to types that can't be constructed, V1 is the generic representation of void. Oh, I was wrong. I guessed. The type with no inhabitants. It might seem silly to provide an eq instance for such type, but it costs us nothing. Consider instances over V1 as being vacuous. If you could give me a value of V1, I claim that I could give you back a function comparing it for equality. Since you can't actually construct a V1, then my claim can never be tested, and so we might as well consider it true. Okay? Kind of strange. Strictly speaking, V1 instances usually aren't necessary, but we might as well provide one if we can. Fine. How come there's no... I mean, unit can only ever be equal to unit, shouldn't I just put underscores there too? What's the purpose of writing out U1 here and then underscore there? What if I replace this with this? Yeah, I just get unused language pragmas, so should be fine, right? The only thing that could happen is that for that to be true, I think. So anyway. The one other case we need to consider is what should happen for concrete types instead of data constructors. Such things are denoted via K1, and in this case we want to fall back on an eq, not geq instance to compare the two. The analogous non-generic behavior for this is how the eq instance for maybe A is eq A fat arrow eq maybe A, right? So we have instance eq A g eq k1 A where g eq k1 A k1 B equals A equal B. Okay, so this is the type quirk of the A, yes? I think that's what that is. So I think this A here, maybe not. I don't really... This denotes some data constructor. That's what it denotes. So this is some data constructor. This is the value it contains. So we fall back on whatever that value A is, or type A. I gotta turn on the... I gotta shut the door. It's really loud out there. Okay, thanks for hanging out for a second. So yeah, so there we go. So that's what that looks like. Okay. But why should we use an eq constraint rather than geek? 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 I'm gonna call it geek. Well, we're using geek to help derive eq, which implies eq is the actual type we care about. If we were to use geek constraint, we'd remove the ability for anyone to write a non-generic instance of eq. I don't understand what that means. Maybe it'll make more sense here in a second. With our base cases complete, we're ready to lift them over sums. Two sums are equal if and only if they are the same data constructor, left or right, and if their internal data is equal. I see. I see what's going on here now. Maybe it'll make more sense to you when I write it. I just peeked at the... Right, so this looks like that sum type before. So it's like weird. All right. What is this complaining about? Oh. There you go. Interesting. Okay, so let's say we had some type of true or false, right? A Boolean. Then we're defining a generic generic eq type class for Boolean, so that if it was like, well, this has to contain something, doesn't it? This would be like either. Yeah, this would be like either. So if we had right, and then we would just promote or lift equal into the values, and same is true for left. Otherwise, it's false. If you're given left and right, for example. So I think that's what that means. And we can do the same thing for products. So let's just delete this. It's going to look pretty close to this. Difference is this is going to be a star. And we have geek A1 star B1 A2 star B2 equals geek A1 A2 geek B1 B2. So this would be like a tuple, for example. So if you had a tuple of, 1, 1, and 1, 1 for a cheesy example, you could test if they were equal this way. That's interesting. Okay, so finally, we want to lift all our geek instances through the reps metadata constructors, since the names of things aren't relevant for defining eq. Fortunately, all of the various types of metadata, D1, C1, and S1, provided by GHC generics, are all type synonyms of M1. Because we don't care about any metadata, we can simply provide a M1 instance and ignore it. All right. Why do I need this? I'm not sure. Probably because I'm going to rely on A's metadata. I'm not 100% sure. M1 Not sure what this is for. Maybe it will make more sense when we do one with actual metadata. I don't really understand what this means yet, so. All right, so this is called step 2. Hang on, I want to put some stuff in here because this is already confusing me. So threefold approach. There's a threefold approach to generically deriving structural polymorphism. 1. Define a type class which acts as a carrier if eq, use geek. Well, prefix type class with G. Okay. 2. No. I can type, I swear. 2. Provide inductive instances of the class for generic data structures. That's 2. I think as maybe when we do this, it will like a few times. It seems like I'm gonna have to do an example here in a second, and hopefully it will become more obvious what's going on here. 3. I got a bunch of text messages or something. I'm sure they're not important. Nope. Okay, and then write a helper function to map between rep and the desired type. So that's the last step. That's what we're doing now. Generic eq generic a g eq rep a head arrow a cool. No idea what this from does. Hang on. I don't know if there's anybody new here. Chat's a little quiet, so I just want to point out what we're doing, just in case it's not clear. Essentially, I'm working on this book right here. It's called Thinking with Types, and it's written in Haskell. And essentially what I do on this stream is go through books and try and learn stuff from them. So right now we're doing type level programming in Haskell. We're also learning about monads in another book called Book of Monads. And like all of this stuff is available on its own. So we're gonna do thinking with types today because I sort of changed my schedule, but I don't know, I'll probably do Book of Monads next Tuesday because on Thursday we're gonna work on a project. So that's what's going on. But today this is what we're doing. I have no idea what this from data constructor does. And they don't explain it at all, so we're just gonna try it and see what happens. So save this. So we should be able to do generic eq true false. Those are not equal. Is that correct? We could also compare probably numbers. It may need to like be explicit about the type. I really don't know. I'm gonna try this though. So generic AA. Interesting. There's no generic int. I'm not sure how to fix that. Maybe we'll learn how to do it in a little bit, but I really don't know. Hello world. Hello. True. Okay. So there's a generic equals function which can compare generics of any type. Now I don't know what this is about. Maybe we'll learn about it later, but I really don't know what it is. So we'll leave that open and we'll go back to Vim and keep going. So generic eq is a powerful step in the right direction. We can define actual eq instances in terms of it. Given our foo data type from earlier, you probably don't even remember our foo data type, but I don't think I even wrote it in here, but maybe I did. Hang on. I didn't. I'm not sure where that came from. Foo ABC equals F naught, F1A, to BC. So we still have to write all this, but at least the implementation is simple. Like, so supposedly this will work. Sorry, this up here. Let's try. FG2, enter, reload. I'm not sure why I have to hit enter, but you have to hit enter. And then supposedly I can compare two foos. So if I do, I don't know, foo. No, it was F0. True. Right, so there we go. Get that. F0 equals F0. F1 true. Whoops. F1 false. And the cool thing about that, right, is that by I didn't mean to close that again. Shoot. By defining all of these pieces, we got that for free. So the Haskell compiler built these generic instances for us, so we don't have to write as many. So I suppose that's pretty convenient if you don't want to have to type a ton. Okay, so now we have an exercise. So exercise 13.2-I. Generic instance for ord. Okay, so step one is define that type class. So we need to define G ord A where I need to look at info ord. So I think that we only need to define compare, so we should have a G compare, I guess. So Z G1 G compare, and that's going to be A X ordering. So instance u1 where. What are the different orderings? Nope. Trying to get used to this. Okay, so less than, equal, greater than, right? I always forget those, so my apologies. So if you have, what's up, Bloomy? Oh, let me put that up there. Show the exercise. EQ, like so. How are you today, Lumi? Tell me about your day. I was afraid chat was broken. It was very quiet in here. Glad to see you. So this is basically writing a generic instance for the unit type, right? So you can think of U1 as this. So doesn't matter what you have, they're always going to be equal. That's the point. G eq B1. I need to move up actually. I don't want to move up too far. Well, I gotta move up pretty far. It's not G eq either. G ord for obvious reasons. And this is G compare. I was writing that verbatim. Very concerned that chat is broken. But it's not obvious to me. Let's just open up this over here, and I can know for sure. Channel. Yeah, that's fine. I mean, the fact that you responded, oh, that's fine. You can be tired. Plus, this is like voodoo magic, so a lot of folks have a hard time watching, which is fine. Or participating or whatever it may be. All right, so that's our void type, which again, apparently we don't need to do, but it's suggested. So sure. What is void again? Well, okay, fair enough. But it can be really hard to understand at the beginning, I guess. Sometimes towards the ends of the chapters I feel a little more confident, but so now we need this K. That's probably true. So we need an ordering to make gord K1 any data constructor and some type where G compare K1A K1B equals compare AB. I have no idea if this is going to work, but it would be cool if it did. Now we need to make this for some types, and it's essentially going to be, what do you return in this case? Do we need to return anything for a sum type for ordering? How do you deal with this case? Do you just return whatever you feel like? And I suppose you can't just return like undefined. Maybe we just return less then? I don't think that makes sense. I don't know what to return. The product type makes more sense, but the sum type, I'm not really sure how to deal with the mismatch. Yeah, I don't know what to do here. And this is like an error. I'm gonna put error here for now. I don't know. We'll just write that for now. Of the default enum instance for some types. Yeah, but generically, right? Like, if you had, I'm thinking of it like, I'm thinking of like either, right? If we have an either, left and left makes sense, right and right makes sense, but how do you compare, or how do you compare a left and a right? You can't. I suppose we could just go look at the ord instance for either, right? There's no reason not to. Hang on. I need this, and we're gonna put that there. So let's just go Google the answer. Ord. Oh, I see. Compare the data constructor themselves. Can you do that? How do I do that? With, there's like an enum function, right? To do that? That's a really good point. That's what we should do. So let's go look at, there's a maybe. Product sum. Looking for either. Here it is. Yeah, so it just derives ord, which means that it's just using the data constructors. So if left is on the left, it's less than. If left is on the right, it's greater than. So how do I... Oh, I just say that, right? I guess we just say that. That's not what I wanted to do. I leave that there. Sorry, I'm still working on my new workflow. It's not going very well. So if it's like L1 anything, R1 anything, that's less than, right? Because the left one's greater than the right one. I think that's right. We can check. And then R1, L1 is greater than. I think that's right. So if we compare true with false, we should get greater than, and false with true should get less than. That's essentially the same thing. But we could also do like right, hello, left, 0. And we should get greater than, and vice versa. Left, 0. Good call, by the way. we get less than, right? So that just, if it can't compare the types, it compares the data constructors. I keep closing it. Gotta get used to it. Pretty hard. Is there any simplification we can do here? I suppose if we don't even need to evaluate these, we shouldn't. So those should probably go last. Right? Because if we put A1 here, we need to evaluate, right? Don't we need to expand the thunk of A1 or up to A1? Whereas if we just match this, we can ignore that completely. Something like that. I don't know. That might be more memory efficient. I doubt it. I'm probably just making stuff up. All right, so this instance is going to be much more straightforward or obvious, I guess. So then we got G ord product where B1 compare A1 A2. How do we combine? What is this complaining about? Oh, yeah, this isn't right. I need to look up how you compare ords. So it's gonna be like ordering. I suppose we can just use semigroup operator. If it then compare singletons. That's in a bunch of weird places. Do we use semigroup? Probably. Is there, why is this zoomed in? Weird. Semigroup, is there one for ordering? There is one for ordering, so we'll just use that, and that comes straight from Prelude, so we can just boop. I'm surprised this is different. I'm just comparing line 57 and 92 for reference. I wasn't expecting this to be different. Oh, good call, good call. Then the question is, oh, it seems like I can use the semigroup there, so that's good. Good call, Lumi. Okay, so there's that one, and then we need to use this metadata thing, which I don't fully understand, so G ord A. G ord M1. Oh. Oops. Okay, and then finally we need generic ord a nope generic a jord rep a Okay, the other thing I want to do is go look up this from function real quick because I don't really know what it's doing. I'd like to just like see its type real quick. Oh, right. It's the from the type class generic. So if you have a generic a, you can write this from, which takes a, it's like pure for a rep. You can think of it like that. Nope, gotta go out. My gosh, the TV is really, really loud. I shut the door and I can still hear it. It's gonna hurt our ears. Anyway. I don't know. So, like, I can get this. So, yes. The problem is that, like, you know, there's no easy way to open this here. I could open link, you know, and it's gonna open in the browser, but, you know, yes. I don't think so. Yeah, I mean, again, it's like that. I mean, that is a file on my machine, so, but, as far as I know, no. Let's go look. Nope, not my workflow. I can do it. What? So the question is, does the LSP I'm using support it? It's not really, you know, if it doesn't support it, then there's really nothing I can do. Yeah, different servers can have different capabilities. So we need to look for Haskell. Well, that's not helpful. Hang on. How did I find this before? Somewhere in here there's a NeoVim RC for this. Yeah, I think you have to define it, but maybe it's defined here. How did that work? I realize that you can't see this, but I don't really know the easiest way to move it. Yeah, so in theory, we're using, I've not done GD before, so let's do that. Definition not found. What I'm using is this one, show documentation. Oh, you're just saying just try it. Sorry. Yeah, GD works, but it just says definition not found. Like it tries to, it just doesn't work. Oh, I see. Okay. Yeah, that works. So see cursor. That will work. Yeah, but it doesn't work for non-local names. That's a good way to put it. I mean, it's nice enough to see, like, actually being able to just go, you know, like this and just open this up probably is pretty nice. It would be nice if it just opened up and I didn't even have to hit open. But like this is local, so it's going to be faster than Google, right? I probably can. I just need to figure it out. Anyway. Okay, so there's our generic ord instance, so I guess we should just try it. It did it again. That is such a habit, and it's quite hard to get out of. Um, um, I mean, that should work, yes? Oh, it is an open issue. Interesting. Right, it's not going to be in there now. So I think that should be this case, yes? No, that's a sum type. No. Ah. We could do something like that. No, that's fine. I mean, that's important. It is important to have. But I don't, yeah, I don't want to do it right this second. Um, hmm. Yeah, and especially in Vim, right? Like, um, I think Vim is particularly bad about that. I mean, for a long time, I couldn't even get it to um you know, you couldn't even get like snippet support and autocomplete both at the same time. Like it just didn't work. So anyway, yeah, the autocomplete's really nice. Why doesn't this work? Right, I should be able to compare. Hmm. I'm falling back into old habits already, let me. Are these not supposed to be here? No, that can't be right. Is this a... I'm very confused. Seems like this should be right. I know what I'm doing. Notice what I'm doing? G compare. Got it. Not on my game today, apparently. So let's see if this works. Left. Yep, that works. So yeah, it seems to be fine. Okay. Next. Yeah, I'm doing the only thing I'm doing wrong is the like I'm having a lot of trouble names today. Like we did the compare thing here, and then I was using G compare and not generic ord. So I'm mixing concepts up for some reason today. Not sure what that's about. I was kind of smashing my head against some stuff today, so maybe that's why. Okay, so this function should give... I'm not really sure how to pronounce this word. Suppose I could look it up. So it's Latin. So nilio? Pronounce. Oh, but I'm not gonna know how to... Even if it shows me the pronunciation, I'm not gonna get it right. Anyway, I think it's nilio. That's what I'm gonna call it anyway. Um, use GHC generics to implement ex nihilo. This function should give a value of just A if A has exactly one data constructor which takes 0 arguments. Otherwise, should return nothing. Okay, so I think we need... Do we need a class? Probably. Because we need to basically catch this case to return... I mean, it's just going to have... It's going to take something No, it's just going to return maybe A on an A. And we're going to basically return nothing for all of these cases except this one. No, it can't be this one, right? Well, it's not going to take two things, right? It's not going to take two things. It's just going to take K1. I get it. Okay, so class GX Nilio A, where GX right? Yes. Okay. So for those of you just hopped in, essentially I'm working through this book called Thinking with Types right here. We're trying to implement some GHC generics, and we're sort of just learning the ropes of making this happen. So this machinery is what's necessary to implement the generic ORD instance in Haskell. So yeah, basically there's a few steps. There's sort of this step here, and then these steps are the middle steps. I'm not going to go through explaining all of them. And then this is the last step. So right now we just finished step 1, I think. And basically the rest of these are going to be nothing except for this one, I believe. Everything else is just going to be nothing. So we'll see if that's actually correct here in a second. So G X U1 where uh this has to take an A, doesn't it? Otherwise this won't work. Eh? I think this is right. Yeah, I think the shape of this generic thing should be A2. I'm not 100% sure. We're gonna try it this way and see what it looks like in the back of the book. Then we have this. Where'd it go? Hmm. I think I'm going down the wrong road here. I really don't understand. Do I have the mechanisms to do this? Mechanisms, probably not the right term here. Do I need another X? So each time up here, we add this X thing. And that's to make this kind work. So am I supposed to have maybe AX? And then doesn't this thing need an A? I'm so confused. I want to peek in the back of the book, but I also don't want to peek in the back of the book. Like, I'm just confused at why this is not. But I don't like that this just says this. Like, if it said, maybe if it said A to maybe A, it would make more sense. Maybe not. I'm peeking. Sorry. Sometimes you gotta peek because you're confused. I'm confused. Maybe I can just get the full type to see if I'm even in the right direction. Okay, so I was kinda in the right direction. I didn't see the whole solution, so we got here. This is where we needed to go. Hang on, I gotta let the cat out. Okay. Um. So how do we put a value there? Well, it's out of nothing, right? So out of nothing implies that it should have like monoid or something. If we force it to have monoid, then we can just use mempty. So let's do that. and see if that's where it's coming from, because I think that's right. In every other case, I think it's supposed to be um, eh, the type A has exactly one data constructor. Oh, I see. I see. So then this implies that this is incorrect. Or is it supposed to be this? No, because this implies that this takes something. So this is also nothing. But then where do I get exactly? Oh, I think it's just here. I think it's that. That's the only one. That's like true or false. And then I guess everything else is nothing. I see what you're saying now. I think. Do I even need to implement these? Maybe I do. I suppose if that could ever happen, we can have it. Do you have the book in front of you, by the way? Or do you just remember that I said that? It's impressive. Oh, that's right. So this is complaining, which means this has to be nothing. There's no other solution. Oh, yeah, yeah. You can just get it. I usually link people to the paid one, but a quick Google will get you there. Hmm. Well, probably need to read the whole error here. How do I get that out, though? I wonder what's gonna happen when I do this. When I save this. That doesn't really say anything to me. Um, so this is quite different than our other cases, right? So do I need to? All right, so so like this AX thing is now inside of a maybe. So I need to get it back to an A. So the only way I can do that is using to. So here we use like from A to promote the type A into a rep A, but we have a rep A and we want to get the value. I know the terminology is a little backwards, but you need to convert that to an A. So to do that, you just, you have maybe AX, so we just fmap 2 in there, and in theory, this should be correct. So if we give this thing a type of maybe bool, it should give me just, I don't know what, wait, no. I can't give it bool, right? Because that's a sum type. I have to give it like a data type with a single constructor with nothing in it, right? Shoot. So we're good. Close this. I gotta get used to this foreground. I gotta use it more during my work. So we'll reload these. And so we want to take X nilio and give it, we can't use true, data A equals A. So X nilio maybe A. Deriving generic. Import GHC.generics. Set X derive generic. Oh, no, that didn't work. I got excited for a second. exactly one data constructor which takes 0 arguments. I shouldn't have done that. This is so hard. Okay, so yeah, doesn't this imply it has one thing? I'm confused. And this is supposed to be unit as far as I understand. So why doesn't that work? Ah, it's such a bad habit. But shouldn't this give me just unit? Okay, I'm gonna go look at the answer. We tried. I thought we had it right, but we don't. Just fine. I'm not surprised we have it wrong, honestly. Control Z. Okay. Okay. Correct. Nothing, nothing, nothing. Well, this type is very, very wrong. Because, I mean, I don't know what I'm doing. How do you know that? How did you know that? You wrote M1 probably. As in pass through to the U1. Okay, so this thing is more powerful than I was thinking, basically. Ah, I see. Okay, so before I had nothing, but this needs to do something with ex nihilo. That's the point. So you basically just need to get M1A. What does this mean? Why would I know to do this? Why would I know to do this? I'm not sure I understand what this is doing. I can't though, because this doesn't take any arguments. Here you can, because or is the point that here I can take one? Or is that not? Okay, you're saying you understand, so I'm gonna let you explain because I'm very confused. I'm also not convinced I should have understood this the first time I saw it. Ow. I mean, maybe I should have, but I don't fully understand this M1 thing. Let's go look at the M1. Because I thought that M1 just had something to do with the metadata. So it's like, is it? So how do you get the metadata back? I suppose you're typing something, so I'm gonna wait a second. I got this part right, so that's kind of cool. But this part was wrong. Although, yeah. Well, actually, we haven't tested this yet. Let's test this real quick. Oh, yeah. Here we go. Reload. It works. It works. This part I'm okay with. It doesn't make any sense to me. Oh wait, no, yes it does. Yes it does. You're right. You're right. Because this doesn't take an argument, the only way to turn an A into one of these, right? Because this is what I need to end up with, is I need to take this and stick an M1 in there. I see what you're saying. So the data type for this is really M1, some garbage, and an A. I got you. Good call. Call. So this is a little tricky because it doesn't take an argument, right? When it takes an argument, it's a lot simpler because you have like AX to an ordering. So you just need to like, call a function. It's very simple. But here we're actually like constructing an M1 from nothing. Well, not from nothing, from a maybe. I understand. That makes sense. This is pretty weird compared to this. Anyway, our implementation was almost right. It's just this one that was wrong. I'm pretty surprised that this just kind of works. If you stick a nothing here, though. I guess a nothing is still a maybe M1 blah blah blah. So nothing still works here. So we only got one piece wrong, so that's pretty cool. I'm happy with that. And if you, again, if you stick a nothing in here, it doesn't look similar to these ones, right? This one is doing something. So if you just stick a nothing in here, you're basically, it seems like you're just sort of shutting down the function. I don't know what the right term is here, but you know, you really need to construct something here. Otherwise, you need to build something here. Otherwise, you get nothing in this case. Anyway, that's kind of cool. I'm glad I got this. You know, that's correct. And I didn't have to think too hard about it. Neat. Okay. So it says, this is about as good as we can do for classes we haven't defined ourselves. However, for our own type classes, we can go further and have the compiler actually write that last piece of boilerplate for us too. We'll get full access to the deriving machinery. To illustrate the point, let's define a new type class, myEq. Yeah, I'm gonna put this to the top now because for all intents and purposes, myEq is exactly the same as eq, except that we've defined it ourselves. This is something I've never seen before. So like, I can provide. Oh, neat. I hate this formatting, so I'm actually going to format this whole code. Although, if I remember correctly, the formatter breaks when I do stuff like this. Because I 100% hate the way this looks. I would rather it just look like this. It's not that long. Oh, okay. So this comes from, by the way, this comes from default signatures. So this is a plugin. I get it. It might. Nope. That's what it tries to do. Yeah, yeah. I think that's the right one. Anyway. I don't love the way this looks, but like it's probably fine. I suppose we could put like space here, and that might look a little better. Because you have like, you know, sort of a default implementation underneath the regular type class. So is this geek my geek, or is this Is this being derived for me? This is, I mean, I don't have a G little league, do I? Oh, I do. Okay, so you do have to define geek, but once you have geek, you can provide a default implementation for a type class. I'm confused. What is the point of this? Oh, this, okay, I get it. Sorry, I'm stupid. If you have this, you can do things like the following. Did I actually, hang on. So with this, you can now, where'd that space go? Now you can do that. Yeah. As long as you can derive generic, you can derive myEq. The hell? Okay, not sure what I just did there. Okay, kind of cool. The next one is pretty involved. We're gonna do this in another file for sure. Oh my goodness. Wait for this. Okay, so yeah, I just have the REPL running, which is fine. So we're gonna start this. Okay, so we're going to generate JSON automatically or something. Not 100% sure what we're going to do. Which derive? I think so. It says I do. You're thinking I can get rid of the myEq and it will have myEq? Is that what you mean? We can try it. Doesn't look like it. If we then do no, that's okay. I'm just checking. I mean, if you got it automatically, that would be really sweet. I guess I don't see how that's possible, but I mean, you don't know what the extensions are doing, right? They can do whatever they want to do. Nope, I'm done with that. jobs. How do I stop these jobs? Oh, once I invoke eek. Interesting. Okay, let's try that. But we definitely gotta comment out. Okay, so let's do this. And then somewhere I need to comment this out, right? And then let's try that. We're done with that file, so we can save it that time. So if we do info foo, it's just a regular old data type. If we then do eq f0 f0, yeah, it doesn't look like it, unfortunately. Can we? Yeah, no worries. I'm curious as well. It's like I don't know how this stuff works. So for lack of a better term, I'm gonna call this gen JSON, and we'll see. We'll see where it goes. I legitimately have no idea. We need about a million trillion extensions. So bear with me while I type these out. Well, let's module gen JSON where? Allow ambiguous types. We need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. It takes a little bit for that to warm up sometimes. Flexible context. Flexible instances. Kind signatures. Overloaded strings. Scoped type variables. Type applications. Type families. This seems like one of those things where we're gonna like kind of put everything together. Type operators, undecidable instance. My goodness, that's a lot of stuff. And we're not done. Control, monad, writer. Yeah, I mean, I've talked about this, I think, with NewMade as well. Is like when we have all of these extensions that we're just kind of using all the time, it probably makes sense to just stick them in there. But I kind of like being explicit about them. When they're things like overloaded strings, it feels like being explicit is probably silly. But like something like allow ambiguous types could be potentially dangerous, right? Like if you didn't know that it was on, you could probably be doing things that you didn't expect. Maybe that's incorrect, but I don't really know offhand when I look at these. You know, I'm still in the mode of like if I see that I need an extension, I just add it. Like it's not a big deal, you know? Yeah. Data, ASIN, value, everything from value. Oh my goodness, I can't type right now. Data kind type. Excuse me. Text and pack. By the way, I have no idea what we're doing. Yeah, point is not have 20 in every file. I agree. This book is like a book of language extensions, so. Sure. All right, now let's work through these. So we need MTL. We need ASIN. We need text. We need vector. We need to refresh this. But this is probably going to take a while, so we should probably just stack build this thing, because we need to compile all this stuff. Oh, right. Foreground, right, all. So the package YAML doesn't get saved, it's being edited in the background. So you need to save it first, and then you can probably restart this, but it's going to take forever, so we should just stack build J10 or something. What? Interesting. It didn't really do what we wanted it to do. That seems like a bug. So we need MTL, we need text, we need ASIN, and vector. That's interesting. I wasn't expecting that. Oh, nice. I already have this stuff all saved, so that's great. I thought I was gonna have to. So if we do that, then everything goes away, and we're ready to go. I would love to explain what we're gonna do here, but I legitimately have no idea, and I suppose it will make more sense here in a little bit. I think we're gonna go over the deriving mechanisms for taking we're gonna build ASIN's generic stuff. Or I don't know if it's in ASIN, but anyway. If we had a data type like so, why? Why? Also, why? Silly man. Okay. Nice. So we're gonna generate automatic JSON instances for this data type automatically. Is there a better idea? Is the better idea just writing from and to JSON instances? I assume that's the better idea. No, we'll see what he says. We'll just keep typing. I'm not about to write the whole JSON schema, but anyway, I think people understand a bit about JSON, so it should be fine. Okay, So when sharing data between Haskell and JavaScript, providing JSON schema as a common format between the two languages seems like it might help mitigate JavaScript's weak typing. Yeah, so the problem is the dependency is the wrong way. Transport interface specifications should drive application source code and not the other way around. Transport interface specifications. Does that mean I should be pulling in JSON? Maybe I'm misunderstanding what you mean. I don't fully understand what you mean, but that might just be because I don't fully understand template Haskell. So it's like, okay, maybe I can figure this out. So you're essentially saying that I shouldn't be writing, well, then I don't understand the template Haskell part. Maybe I'll clarify. I know you said you're tired, so maybe it will become more obvious as we work through it. But maybe not, because I don't know anything about template Haskell. All right. Writing JSON schema by hand is no fun, and so we find ourselves with a motivating example of generating code generically. The mouthful, kind of. As always, we begin with a definition of the carrier type class. Such a thing needs to produce a value, ASIN's representation of a JSON value. Okay, so, oh. Okay, so it's like, keep the schema and the source code separate, and right now we're sort of merging the two together. That's what you mean, I think. So it's like your transport protocol is outside of the source code instead of inside. Embedded in Haskell, like a DSL or something. Okay, so I think I said that right then, in theory. So we're gonna write this thing called G schema. Approximately, anyway. I never say anything as well as you do. Okay, so a writer, if I remember correctly, I actually forget how the writer works. So let's go look at it. So CD. Now we're gonna have an issue, right? Because we have, yep, where this is too long. Nope. Unfortunate. What is W? The output to accumulate. Output to accumulate. I've never used writer, so this might be a little weird. So this is the monad we want to work in, and this is the output we want to accumulate. So I'm guessing a value takes in this. That's what I wrote. Package ASIN. It didn't work. Silly. So a value is going to be string. Well, it's called a string, but it's actually text. It's kind of funny. Interesting. All right. Whoops. That's not what I wanted to do. I'm really bad at this today. I can't get my workflow straight. If that's not clear. Okay. Anyway, notice that gschema doesn't reference the A-type parameter anywhere. Well, we could use a proxy to drive the instance lookups the way we did for hasprintf. A cleaner interface is to allow ambiguous types and later use type applications to fill the desired variable, excuse me. For our purpose, we will assume we only want to generate JSON schema for Haskell records. In fact, it will be an error to ask for a schema for any sum types since it's not clear how to embed them into JSON. Before diving in, we'll need some helper functions for manipulating JSON objects. For example, we'll want to merge two of them by taking the union of their properties. Okay, we can do that. So merge objects. Going to take two values and produce a value. All right. Is this so because you know I'm a monster? No, this would be like, that's not right. That's not what I'm looking for. I want to write this in point free because I think I can. But I need to go Googling. We have like two objects, a function. Hmm. The type of this. Oh, actually. This should be right. ABC is really AAA, and I have FA, FA, FA. What? I'm confused to why this doesn't work. No, it doesn't look like a functor. Right. Not the right shape of functor. Right. So what is an... I'm confused. What is this thing then? Why do I not have to match on these? Anyway, I understand why this doesn't work, so I suppose that's important. Isn't this an incomplete match? Because I'm not doing it for the other types of values? Yeah, no, it wouldn't make sense for value to have a functor instance, right? Because it doesn't have a type parameter. It can't, by definition. So this is an incomplete definition. Wonderful. Okay, we'll go from here and see what happens. I'm not really sure. I don't really understand why this is incomplete. Um, known symbol. Known symbol. Oh, okay, so I think tell gets us the writer, this shape basically. Yeah, Oh, okay. So yeah, so we need to give it an item, which I guess is going to be a list of text, considering we're using pack. Pure gets us the empty list, or well, turns it into a list, I guess, because it must only have one element, and then it sticks it in a writer instance. I'm guessing. Yeah, okay, so symbol val takes a known symbol and converts it to a string at the term level. So type level symbol to term level string. Then we pack it, right? So that converts it from a string to text. Pure gets you the list, tel gets you the writer. Wonderful. And I mean, we can look at that, but there's pack, string to text. This pure is going to be specialized to a list. See? And then tel is going to take, whoops. Tel is going to take a list of text and embed it in a writer with in the unit. No, it's in the, that's the secondary monad. Yeah, anyway. Okay. Omit required. What does this do? So save this. Control Z. Jobs. We don't have stack running, so stack REPL. Then we are going to write run. Shouldn't I have run writer? Oh, I'm such a doofus. Ay, ay, ay. Yeah, you could see like I start to get useless around. Well, I did some useless stuff, but I do start to get useless around 2 hours. So simple things stop making sense. But that's okay. There's like a symbol for enter, and I thought it was a line continuation. Well, no, it is a line continuation. But anyway, stupid. Don't worry about it. So symbol val is a function that converts a symbol into a string. We already know that. It comes from that typelets package, which we. Oh yeah, if we use exec writer, that will just get rid of the unit at the front, right? Yeah, that'll just get us the value. Okay, so the known symbol stuff in symbol val's type is simply a proof that GHC knows that's what symbol we're talking about. It will automatically generate the known symbol instance for us, so it's nothing we need to worry about. Anyway, in JSON schema, the Boolean type bool is represented via Boolean. Along with the same vein, integral types are integer, but all other numeric types are simply number. User types should be serialized with their given name. This is a good opportunity to use the closed type family a closed type family to convert from Haskell type names to their JSON schema counterparts. Well, it should just be FG1. We will refocus. So some boilerplate going on here, but that's fine. We are using a type family. We're using a type family to generate some of the metadata, I think. So it says there's no straightforward means of getting the name of a type as a symbol. We can use generic metadata to retrieve a type's name. We're not using that there though. Where do we use this? Oh, right. Okay. So what we're using this for, remember that we're actually generating the JSON schema for our data type, not the JSON itself. So like if you have a Haskell type, it's only the schema that describes the type. So let me bring this up. So in JSON schema specifically, if you have a string, that's called a string in JSON schema. If you have an integer, that's called integer. If you have an array, a list, that's called an array, etc. So we're actually generating JSON schema, not JSON. So I think I said that wrong when we first started. I'll fix that in the name. True JSON type name A. It'll probably correct itself when no. I don't know where this comes from. I thought this would come from typelets. No, I can just do down. So type name. Probably not from that. Oh, we're implementing this. I'm a doofus. My apologies. I'm gonna have to get further along before I can explain any of this, because I can't really yet. Okay, so this is in the metadata, that's a representation. So what we're trying to do is basically get a symbol from this, and I think we're just gonna do. All right, so you were saying before is that you're using template Haskell because it gives you access to these things, right? In a lot simpler way. Is that correct? So we're kind of doing the same thing. It's just that it's probably easier to get these things in template Haskell, not directly. Interesting. Okay. I've seen a little bit of template Haskell. Soding was using it on his stream, so I know very, very little about it. I know that it exists, but I'm not using it. So essentially, the whole point of this machinery, for reference, is so we can get to the following: kind to JSON type person. Idea is that the semantics of JSON don't align well with data declarations in Haskell. Because, okay. Fair enough. Anyway, the whole point of that last bit was to get this. So that if we had, you know, like the following, you can say that a list of persons is an array, or a person is a person, something like that. I'm surprised this is not recursive, but maybe that's part of the. So I don't like specifying it with data declaration, but using true JSON specifications to then generate data types from. Start with schema, generate data type. I think I understand. So you're saying, like, give me a JSON schema file and I'll generate you a Haskell data type. Not start with Haskell data type and I'll generate you a schema. That's the difference with what we're talking about. Assuming I said that correct, then I think I finally understand where you're coming from, because I didn't before. Okay. Yeah, fair enough. Fair enough. As long as it's like you're defining something that's, JSON schema somehow. It's not this, because this is not JSON schema. You need something to embed. I think I understand better. Okay. So it says something we'll find ourselves generating often are objects of the form. What's is a JSON object is just this, right? So like if I had, whatever key value, do I call this a JSON object? Oh wait, but they got to be double quotes. So I think that this is would be called a JSON object. So we need to write these essentially. We're going to write a function for that. Make type object. Strong. Yep. Yeah. So that's okay. I think I understand now. Or at least anyway, I'm closer to understanding. All right. So this one is saying like, look, if you give me two JSON type A, or something with the constraint that two JSON type A is a known symbol, I'll give you back an object which I suppose comes from ASIN itself. That's just like this, essentially. And I guess if you give it a list of objects, it will give you commas between these or something. We can try it real quick because I really don't know. So we want to say object list key dot equals value. Oh, sorry. Pack. What do I need to pack? Everything. Or I can just set overloaded strings, yes. Oh. This is from list for a hash map. Okay. So this is a pair. We give it a list of pairs and it generates a value. Interesting. I've not used ASIN a lot. I mean, we've used it a little, but not a ton. All right, what time is it? 10 o'clock. We got a half hour. See how far we can get. So anyway, using this like this, hash map text value. Wonderful. Yeah, so this from list is just the from list from hash map. And then we got basically text, and this is another value, right? Because it's a string, which means it's a value. That's the data constructor from value. Cool. And I assume oh, I was like, what? It takes a text and then a V that can be turned into JSON, so string. You know. All right, let's do it with the weird. Yeah, so here's the schema. So you have a type for int is an integer. Neat. Okay. So let's move this. Okay, so now we're building the properties object, which means what? Too far, too far. Not far enough. Where did this go? So the properties basically define each type. It basically contains all of the type objects with their, yeah, it contains all of the type objects. I'm looking in the wrong place. Hang on. Okay. We're gonna have to use this one somewhere. I think we're gonna use this one recursively at some point. Okay, so it says make property object is intended to be called with a type application. It takes a symbol corresponding to the name of the property to admit. These symbols will come directly from the rep of the data structure's record selectors. Right, so there's like a list of the record selectors in the metadata itself. In order to get access to the record name, it's insufficient to simply define an instance of gschema for K1. By the time we get to K1, we've lost access to the metadata. The metadata is stored in an outer wrapper. Instead, we can do type level pattern matching on M1S meta K1 underscore A. The S type is used as a parameter to M1 to describe record selector metadata. Oh my goodness. Okay. Anyway, this is step 2. Like, this was step 1, I think. Well, the rest of this is all helpers. That was step 1. Guess now we're getting to our instances. G schema M1 S meta cell just yeah, you can't even see this. Hang on. Okay. I'm supposed to know how to do this for reference. Whoa. What the hell is going on here? This is absurd. I'm not even sure what I'm looking at. We'll look at an example here in a second, but my goodness, this is rough. And there's also not a ton of explanation. So, in order to get access to the record name, insufficient to supply an instance of G schema for K1. By the time we get to K1, we've lost access to the metadata. Metadata is stored in an outer wrapper. Instead, we can do type level pattern matching on M1S meta. That must be this meta selector. K1. Well, we did see this. We did see this in the metadata somewhere. So, like, this is the record constructors, plural, one? We'll see in a second. And A is the data constructor. So this must be this is the record constructor. That's the data constructor. Well, the type of the data in the record constructor. Yes. Yes. My gosh. All right. I did it again. I don't know where one went. Okay, fine. thing that sucks about this is I'm gonna have to do a ton of we're gonna need yeah. Then we're gonna need a bunch of imports to try and use this thing. Why do I not have I don't know why do I need byte string? Why do I need lazy? I need this. I'm so confused. I'm also extremely hot. It's very warm in this room. When I shut the door, there's essentially no air conditioning in here. Why would I want to encode this? It's like you have this function called encode pretty. Yeah, it's actually cool here. Like it's not temperature hot outside. It's just really hot in this room. Mainly because I run warm generally speaking. Um so I want to look up pretty uh and we want to look it up. What kind of printing function does ASIN have? Oh, encode, I see. So encode takes a value. But why would I don't understand why I'd use I'm very confused at why I need this. Oh, well, that's right there, because I'm going to get a byte string back. But it seems like if I just encode it, it just gets me this. So why do I need to use this weird encode pretty function and this lazy byte string printing function? I don't know yet. Let's just go find out. Sorry, I'm getting very sidetracked. Um Okay, so now I have this, so I could just encode it. But I need to get encode, which probably just import data. Oh, yeah, that would be great. So data ASIN text encode to lazy text. Oh, I see. So like I can encode it to some byte string like this, but this is fine, right? I mean, this is more or less visible. It would be nice if there was just a pretty printer that wasn't an encoder as well. Although maybe if I just encode, so I don't even know where this function is. Like, there's no encode pretty, is there? I mean, I guess I Googled this, right? I'm very confused right now. Encode pretty. That comes from YAML. This comes from something called ASIN pretty. Which we weren't. Okay, so I don't care about this. Basically, this is just nonsense. This is totally fine for me. I can see it. I see Jason, folks. Good enough for me. Anyway, he just had it pretty printed, that's all. It was, I don't feel like going to look for this. I mean, even if we just encode, wasn't that enough? Oh, import data ASIN. What does that look like? Same thing, right? Same exact thing. So, no big deal. All right. Sorry about that randomness, but I don't really know what to do there. FG jobs. What are we at? Because I keep screwing up. I have no idea what this inline is for. But apparently we need it. I think this is the last one I'm going to write for the day. G, and we'll come back, I don't know, at some point and keep working on this. G schema. So we're going to talk about products, right? Which is our record type. Wow. Neato. Gonna have to think about this one for a second. All right, so if we have a product of, let's say, for lack of a better term, or not, well, not lack of a better term, but if we have a product like a tuple and it's got an F and a G in it, we need, so this is the application of the type itself. Wild. And this gets us this writer thing. So yeah, okay. So we need to F map over this value. which is why we're, yeah. So we partially apply merge objects to the result of G schema at whatever our first product type is, then combined it with the other side. Weird. Please show me an example of this. Oh, okay. No example of this. So anyway, we're gonna stop here. But what I want to do real quick is see if I can figure out how to use this, and then we'll go from there. Maybe we can't use this yet. Maybe that's the point. Let me read a little bit further. I don't know. My goodness. Okay. Well, actually, we're almost done with this part for the schema. And then one thing they're talking about is performance. Oh, actually, they bring up template Haskell, Lumi, towards the end here. So we'll see how. And apparently, it's like literally. Wait, impassably. I don't know what this is about. Anyway, talk about con extensions or why. And then we get to index monad. So anyway, we're almost done with this chapter. And then there are literally 2 chapters left. One called. Wait, chapter 14 is called index monads. Chapter 15 is called dependent types. And we're done. So there's actually only 2 chapters left in this book. So again, we're working on this book. So you can buy the book. You